Just over 100 years ago, a physicist named Albert Einstein predicted that something out of the ordinary would happen when two celestial bodies, could be planets, could be stars, orbited around each other. He predicted that with his calculations, that massive accelerating bodies, neutron stars perhaps, or black holes orbiting around each other, would actually disrupt space-time. This disruption would cause waves, very much like the waves that you see in a pond when you throw a stone into it. They spread out. Well, these waves, these ripples, are called gravitational waves. And he included the concept in his general theory of relativity, which he published in 1916. These gravitational waves are invisible and they travel really, really fast. It took about a century to prove that Einstein was right. How do you detect a gravitational wave? And more importantly, how do they inform us about the universe? For answers to these questions and much more, we welcome our guest, Karl Rijkse. Paul is an analytical and organic chemist. He got his degree at the University of Amsterdam in the old country. He then moved to London, England, not Ontario, where he went to the Hurley Management College and earned an MBA in strategic management. His last position was as Vice President of Technical Sales and Research and Development at Tiger Coatings. Karl has had an interest in astronomy for a long time, and he has belonged to a number of astronomy clubs over the years. He is currently the Vice President of the Shoreline Amateur Astronomical Association, which is based at Hemlock Crossing Park. And without further ado, I hand it over to Karl. Thank you.
Thank you, Luis. Thanks for your nice introduction, and you gave my half of my presentation away, so that saves me time. As I'm joking most of the time, I'm indeed from Amsterdam, so you hear a slight Dutch accent. I'm from the real Holland. The morning, and I was very surprised about the amount of people that signed up for this. It is not a day-to-day topic, I would say. We will catch up a little bit on Einstein's theory, also on quantum mechanics, cosmology, what is the concept, what we have now of how we came where we are, and physics. So yeah, it's a challenging journey. Before I do that, as Luis said, I'm part of the Shoreline Amateur Astronomical Association, so SAAA, so otherwise I break my tongue. As club, we have a very nice setup, and I'm very happy that you are making use of that. Not only because of the presentations that we do here, because Frank in the back gave a presentation last year to you about telescopes, but you also visited already our observatory at Hemlock Crossing, where we have every Friday night when it is clear. And that does not happen too much in Michigan. Since the beginning of November, we had to cancel all Friday nights because of clouds. But we have a very nice observatory at Hemlock Crossing, and last year we had 1,600 people visiting us. Next to that, and I heard from Luis this morning that the 2 visits to the planetarium at Marketa Bay Middle School, we have access to a planetarium, and they put in a brand new digital planetarium in September. Those 2 visits are booked full. That's also where we have our membership meetings and where we have a nice set of telescopes that people can lend, as well as a library specifically to astronomy. Last year, you might know, was a solar eclipse, about 95% in Michigan. I went to Missouri to see that, but this was the crowd that attended us last year. So yeah, as a club, we have nice resources, and I'm very pleased to see that you make use of it. Things change quickly. I'm not the VP anymore for SAAA. The former president is sitting there. The current president is here. So he appointed me to be VP and then moved me to the president's spot. My presentation is in two parts. So first I will talk about gravitational waves, taking a look a little bit about the physics behind it, and also how are they being measured? How do we know that they're there? The second part is about composition about the universe. You might be surprised to know that what we see as light, UV radiation, infrared, X-rays, is only 5% of the universe. The other 95% is what we call dark, maybe because we don't know what it is. So to jump into gravitational waves, as we mentioned, Einstein, probably the most famous physicist, thought in his theory on general relativity that gravitational waves must exist and that they are changing the form of space-time. In his opinion, because those ripples are so tiny, he thought at the time that they could not be measured. And it is a ripple of space-time. So space itself, and think about a rubber sheet. When you put a ball on there, that rubber sheet deforms. And that rubber sheet is basically the space-time. You can imagine that as space-time. So even a light wave that crosses that space-time, that rubber sheet, will go with the space-time. So if you walk here down 8th Street, you have probably the imagination that you walk straight, which is not really true. It is tiny, but you are walking over the curvature of the Earth. Same with a light wave going through space where there is mass, like the sun, or a black hole, or a neutron star, that will go with space-time. The first really observation of gravitational waves and a confirmation of that was when two neutron stars were spinning around each other. And I will come in a later slide about what a neutron star is. So when two stars, like neutron stars, which you can imagine as the mass of the sun in a diameter of Earth, very compact, a lot of mass. A spoon of a neutron star would weigh 100 tons. That's roughly the equivalent. So when they are rotating around each other, we can measure exactly the decay in the orbit of those two stars. That was first measured in 1974, and the decay of that orbit was exactly what Einstein predicted in his theory. And that was basically the first real confirmation that gravitational waves exist and that they are taking away energy from the orbit. And that the two neutron stars are circling around each other in smaller and smaller orbits. So this is how you can imagine space-time being deformed. This is, of course, an exaggerated picture. Earth is not that heavy. But again, it's a fabric that is really changing space-time. If we talk about gravity, we also have to talk about quantum dynamics. Because the question is still, if gravity is really a force. We know for sure that there are three forces in quantum physics. One that is dealing with what they call the strong force. Let me see, I have a pointer here. So the gluon and the quarks are basically in the strong force. If you have a proton, and I know we have a lot of chemists here, if you have a proton that is made of an up and a down quark, I think two ups and a down, and the neutron is two downs and an up. And the gluon is the force carrier of the strong force. Like for light, the force carrier is the photon. We have also the weak force, which is carried by the Z and W boson. And that creates radioactivity. The electron and the electron neutrino are combined with the up and down into atoms and molecules. So this picture stands like a rock. In 2012, in the CERN Hadron Collider, they confirmed the Higgs boson, which was already calculated and predicted in 1964 by Peter Higgs. And this picture stands like a rock. Up till today, all experiments are confirmed in quantum mechanics. Like a separate pillar, relativity, Einstein's theory is confirmed up till today in all measurements. The problem is combining those two into one overall theory. And that has not happened as of yet. Talking about gravity, we do not know for sure that gravity is a force. All other forces go two ways. Gravity is only attractional, not repulsive. The question that scientists are asking is gravity like temperature, something coming from somewhere else. Temperature is basically the movement of molecules. The quicker they move, the more heat, and we measure that as temperature. But temperature is not something that exists by itself. Is that the same with gravity? We have never measured gravitons. We predict them as being the particle that carries the gravitational wave, but they have never been measured. We know that space-time is being curved because we see what we call Einstein rings. And only in 2017, we got a confirmation that gravity waves are traveling at the speed of light. Again, that could predict a particle carrying that, but that's not sure. You see an Einstein ring. You see in the middle a very heavy galaxy that contains a lot of mass. And light from behind that galaxy is distorting another galaxy. So if we have Earth, we have the heavy galaxy, right behind that is another galaxy, and the light is bended because of space-time towards us. Yeah? So we're looking straight at that galaxy. And behind the galaxy, the heavy galaxy, is another galaxy, and the space-time is distorted. I need to talk a little bit about star evolution, because I will talk about neutron stars and black holes, and just to make sure that we understand what is happening. So if you know beautiful pictures from the Orion Nebula, That's a kind of nebula where stars are being formed, mostly in groups. So our sun is an average small star in about 5 billion years. So don't lose sleep over it. It will expand into a red giant when it has burned through its hydrogen and helium. And it probably will expand up to Mars. So Earth will not exist anymore. It might form a beautiful planetary nebula, and it will end as a white dwarf. So it will compact itself smaller and smaller, and the outer layers are blown off as a nice planetary nebula. And it will be a sinter, and it will cool down and cool down and cool down. Much more interesting is what's happening when the star is big. And there was an Indian physicist, Chandrasekhar, who in the 1930s already calculated what would happen. There are two scenarios based on the mass of the star. It will end up as a red supergiant, so expand really, really far out. And depending on the amount of mass that is left after a supernova, where the star is really exploding, because there's always a counterbalance between gravity and burning off elements, which is counter to gravity. So when that equilibrium is not there anymore, the star will collapse, will blow off its outer layers, and that goes very, very fast. And then two things happen. When the star that is left is around 3 to 4 solar masses, it will collapse into a neutron star. So there's a star, as I mentioned, the diameter of Earth, but with the sun as its mass. So all the elements are crushed into each other, and basically protons will end up as neutrons. That's like the theory that is there at the moment. So that's why they call it a neutron star. Only neutrons are left as elementary particles. And the pressure is enormous. And we see those stars as lights in the universe because they have gigantic, strong gravitational boundaries. They're called pulsars, and I will talk about pulsars later because they're very important in measuring our universe. And they're like the lights we have here on Michigan coast. We see their light beams on and off. So they're rotating with high speed. Even those neutron stars, despite the fact that they're the size of Earth, rotate 300 times a second. Oh, too quick. When the mass is higher than about 4 solar masses, the star ends up, as we call a black hole. Why do we call it a black hole? Not because we don't know what it is, but because light cannot escape. So the black hole has what they call an event horizon. And at that event horizon, the gravity is so strong that light cannot escape. Mr. Hawking, Stephen Hawking, in 1974, did nice calculations about black holes, and they still evaporate. So still a little bit of radiation is coming off that, but that is minute. Nevertheless, light at that event horizon cannot escape. So when you fall in or light falls into that, or any particle, anyone falls into the black hole, there is no escape possible because gravity is so strong. And these are the mergers where our gravitational waves are mostly coming from, and that's what we are able to detect them. So if we take a look at gravitational wave spectrums, there's a range. We go from universal size, where we talk about, and I will explain all this in later slides. We talk about the cosmic microwave background, which basically originated in the birth of the universe. And we have measured that with the Planck satellite. I will talk about the pulsar timing array, because as I mentioned, neutron stars spin with very high speeds, and their beam of radiation, because of their gravity, like Earth has a north and a south pole, has a very strong gravity force. It's about a Tesla. Neutron stars, we talk about gigateslas. And that energy has to go somewhere. So we see that as a flashlight every time rotating. The frequency of those gravitational waves in this area we can measure with space-based observatories. And they work on that. I have an example of that as well. And observatories from the ground, like LIGO, is able to measure in this area. Which is good, because in this area, we take a look at mergers of black holes and neutron stars. If we talk about this spectrum, like the CMB, so that's a cosmic microwave background, we talk about galactic scales, and the pulsar timing also on galactic scales. So one of the arrays that made a measurement on the pulsar timing, and that announcement came out basically 3 or 4 months ago, they worked on this for 2 decades, and they measured pulsar timing. As you can see, it is a global corporation with radio dishes from all over the world. As you probably know, unfortunately, Arico has collapsed. I think about a year ago that collapsed. And I read an interesting article how that happened, because nobody knew exactly why. It is in Puerto Rico, and it managed to sustain several hurricanes. But a couple of years ago, the tower on top collapsed into the dish, and there's no money to repair it. But the theory now is that there are some towers holding up the detector. They added a very strong radar system in the beginning of the year 2000 to that system. And it seems that the strong radar waves gave zinc creep, caused zinc creep in the pillars that were holding up the detector. And because of that zinc creep, the tower collapsed, which again is very unfortunate. As you can see, a global consortium. And what are they doing? Since all the observatories are located all over Earth, you can measure the difference in timing of a pulsar coming to you. You need to imagine there are about 20 observatories. All the timing needs to be aligned. You talk about picoseconds of time difference. But when a merger is happening, then basically the pulsar, or no, let's take a step back. So gravitational waves are penetrating the universe. A pulsar is giving off a timing, and you can measure exactly the time between each pulses. With the global setup, the timing in the United States or in India or in China will be different. That's also the way how we measure what they call parallax. You do trigonometry with measuring now a star, and you measure it in 6 months when the United States is on the other side. You measure it again, and you can measure exactly where the star is, what the distance is. That's the same how they do it with pulsars. Again, the measuring needs to be very precise, and they measured about 70 different pulsars all over the sky. And what they found is that there is a shift, a statistical shift in the timing of the pulsars. So again, in a different picture. So gravitational waves are throughout the universe. And these are gravitational waves that are coming from galaxy collisions, are coming from black hole mergers, are coming from all over the universe. They predict even that these are ripples from the beginning of the universe, where you can see a kind of what they call a sound effect in the universe, rippling through the universe. So these are gravitational waves that are throughout the universe, not specifically for one merger. And again, it is the timing, the pulsar timing that we measure on Earth that gives a clear sight of those gravitational waves rippling through the entire universe. So again, if you take a look back at this picture, then we are in this area of the frequency of the time scale of gravitational wave. The facility that measured the first gravitational wave on Earth was LIGO, Laser Interferometric Gravitational Wave Observatory. And there are two sites, one in Livingston and one in Hanford. So they're about 2,000 miles apart. The reason is, if one observatory measures something, did it really measure a gravitational wave, or was the truck coming down the road? Because when you measure a gravitational wave, is this it? Or somebody closing a door? That also shows that in the first 10 years of measuring, there was no measurement. It was not because the setup was not good. It was not good enough, not precise enough. The second run, where they upgraded the detectors and upgraded the mirrors, it did not take long for the first measurement. And it took them another year to announce it, because they wanted to make sure that was real. What they also do on a regular basis is do dummy runs. So somebody initiates a kind of a detection and see if the scientists find out if it is a fake or not, just to keep them sharp and make sure that they measure correctly. So there are two sides, again, to make sure that when one side measures something, that the second side confirms the measurement and sees the same thing. Third run started in 2019. That's also where the most detections came. And the fourth run, and every time there is several years of upgrades and several years of maintenance, the fourth run is still running and will end next month. LIGO is extreme engineering. There were 3 people getting the Nobel Prize for this in physics. One on the idea of how to measure this, and the other 2 on how to set up the equipment to measure something like this. We talk about 2 L-shaped detectors, which are about 2.5 miles long. And we talk about a difference So you have two L-shaped long vacuum tubes, and you talk about the difference in going back and forth of time, 10 to the minus 18 meters. That's even in feet, very small. So they measure a difference of 10,000 times smaller than an atom. And that's the smallest measurement ever done by science. The strain on the mirror, which is 10 to the minus 21, is so small that they need to calculate quantum effects on a mirror. They have a laser going through the vacuum tube, bouncing off of the mirror. And with those kind of dimensions, they need to calculate the bounce of the laser light onto the mirror. There are quantum effects happening there. Basically, the laser light is pushing a little bit. Normally, it's not a problem for us. It's a problem for them. So they need to calculate those kind of things that are happening in their measurements. So this is one of the LIGO sites where here in the white building are all the detectors. These are vacuum tubes. And at the end of the tunnel is a mirror that bounces back the laser. So how do we measure that? The laser is also not an ordinary laser. If you point the laser at the end of the wall, for instance, you see a nice dot. But the dot is way too big because my laser light is not in frequency completely. They need a laser light that is completely in frequency. So they strain that laser light to make sure it has one amplitude. That laser light is bouncing from start onto a mirror system. I will show you that in a moment. Going and being split between the two mirrors at the end. So when nothing is happening at the detector, they don't see anything because, as you know, light, the same frequency, is canceling out. So the detector will not see anything. When a gravitational wave is rippling through, and again, we measured 10 to the minus 18 meters. So it is a very tiny shift in either one of those tunnels because the entire system, the entire tunnel will shift. We will shift, Earth will shift. We don't feel it, we don't know it, but it happened. So when the laser light is not in frequency, so it's out of sync, then the detector will measure something. So they are very, very sensitive measurements. And again, even when somebody is closing a door too loud or a truck ripples down the road, they will measure it. And between all that noise, they need to filter out the gravitational wave. So this is the easy setup of splitting a beam of laser light and making sure the frequency is perfect. Here we have a mirror, and that mirror has a specific suspension system and also hangs on special ultra thin titanium wire. The wire is thinner than a human hair to make sure the mirror does not move when a truck comes by. So, I mean, this is exceptional engineering. So what do we see when a gravitational wave is rippling through that system? And what can we tell from it? The amplitude gives way of the fading of the gravitational wave, as well as the mass and the mass of the black holes. Yeah, the more massive, the stronger the waves, and also the spin and the angle, because even black holes spin. And ideally, when you have a neutron star or a pulsar, you have the light coming towards you, but normally they're on an angle. So even that they can see from this amplitude, from this period. The in-spiral, and you see the frequency getting higher and higher, the in-spiraling of the two black holes, like could also be neutron stars, says something about the orbit they're around. And the closer they get, of course, the more spin there is, the more energy they lose because of gravitational waves, and the higher the force. The mass determines how quickly that in-spiral is happening. We talk about milliseconds here, despite the fact that we talk about black holes, which have 40 or 50 or 60 times the mass of the sun. In their last orbits, we talk about milliseconds. Then we have at the end a kind of ring tone where the merger is happening between two black holes or two neutron stars. So two bodies are merging into one another. And a lot of energy at that moment is lost in terms of spin and in terms of gravitational waves. A lot of energy goes out into gravitational waves. So this is the kind of spectrum you expect when something is merging. The first merger was announced, or measurement of merger was announced in 2015, so that's already 10 years ago. Because we have two locations, they can measure roughly from where it came. So that was in one of the Magellanic Clouds. There are two Magellanic Clouds, a small one and a big one. There are two dwarf galaxies that are rotating around our own Milky Way. You can see them with the unaided eye in the southern hemisphere. I just came from there. The merger was about 1.3 billion light years away. So it took light and also gravitational waves 1.3 billion years to reach us. And as I mentioned, the merger was quick because the last 5 orbits, and imagine a 29 and a 36 mass black hole. So 29, 36 times the mass of our sun. The 5 last rotations of that merger happened in 0.2 seconds. So that are very violent mergers. I would not like to be there. It released 50 times more energy than the light we can see in the universe. And a new black hole emerged with 62 times the mass of our sun. And 3 solar masses were lost in gravitational wave energy. And this is how it looked like. So we have Hanford and Livingston that were basically the first ones to measure this, where you can see that there is a difference in signal strength between Hanford and Livingston. And that has to do with the orientation, Washington or Louisiana, the orientation towards the sky. So you get a stronger signal when you have a better orientation. Virgo is a observatory in Italy, Europe. Again, you can see here the stronger signal from Livingston, and here you see exactly as predicted and as calculated the kind of graph you expect when you see merger like this. Here's the timetable in seconds, and here's Was it? Doesn't matter. But you talk about 0.46 to 0.56, so this is 0.1 second when this all happens. Very quick. So you need to pay attention when you do measurements like this. It's gone in the blink of an eye. We're building more observatories, which is good because then we can do calculations exactly on where those mergers are happening. So I mentioned already the two in the United States. The one in Italy, Virgo, this is a smaller one in Germany. We have Kagura in Japan. And at the moment they're building LIGO in India, and that should be finished next year. So the different runs that happened over time, you can see the difference in the equipment and in the sensitivity, what they can measure. On the first run, they basically were not able to see anything that had to do with the sensitivity of the equipment. The second run was already much better, and MPC stands for megaparsec, so that's the distance how they can measure. I think 1 parsec is about 4 light years, if I'm not mistaken. And the third run was the most successful. And again, the higher the number here, the farther they can see out into the universe, but not only that, the more sensitive they're getting for even smaller mergers. The next run should be somewhere starting in 2028. And again, this is all upgrading mirrors, lasers, sensitivity for measurements, etc., maintenance. This is at the moment the sensitivity they can see. So here you see the mass, solar mass of neutron stars and black holes. So this is the boundary of sensitivity they have at the moment. These are mainly mergers of neutron stars because they're smaller in mass compared to the sun. And these are black hole mergers. So as mentioned, the third run was the most successful. Here you see the different measurements they have done, where for instance here, merger of 2 black holes, which resulted in a merger of a new black hole with a defined mass. So yeah, this is not one measurement. They have done a significant amount in the meantime. And yeah, that gives us, or let's say astronomy, I talk about us, it's not me, it's just presenting. But that gives, next to all the standard stuff we measure, like X-ray and gamma ray and UV and infrared and visible light, gravitational waves gives a new light on what is happening in the universe. I mentioned space-based antennas because the advantage here is twofold. A, you have no gravity, which is advantageous compared to Earth if you measure something like this. The other thing, the distance. So here they are planning 3 satellites to fly into space in a triangle, and they can put them as far away as they want. On Earth, we still have a space issue, and not only a space issue, but also the curvature of our Earth. Livingston and Hanford and all the other facilities can only have a certain length before the curvature of the Earth is coming into play, because you can point a laser 100 miles away, but your detector needs to be somewhere up in the sky because the laser goes straight, but the Earth doesn't. So advantages in space, you can put them as far away as possible, and then you also have an increased sensitivity. But there is, of course, a challenge. And they did a concept flight with satellites, and they called it LISA Pathfinder. And they made two identical 2 kilograms gold platinum cubes. And I kept them a certain distance apart. So they flew in one satellite, 2 gold cubes. Talking about influences, despite the fact that you fly in space, in the satellite, it's not perfect vacuum. There's still some left air in there. I mean, it gets less and less over time, the longer you fly the satellite, but still, gas molecules are bouncing off, and that disturbs the measurements, despite the fact that there are only a few amount. And the test masses must be very, very consistent, motionless. 1 part in 10 million, a billion. They were very successful because you can see here the first concept. This is what they hoped for, and this is what they got out of it. So again, this is the gold cube with the platinum hanging in a frame. The precision was excellent. Not only the dimensions of the 2 cubes, but also to keep the distance from each other. The most disturbance they had was with keeping the satellite exactly pointed to where it needs to go, so off the sun and the earth. And there was some noise generated by the gyro to keep the satellite in place. But the concept stands, and the European Space Agency, so ESA, is working together with the Japanese and US and Canada to make this work, and they think they launch this somewhere in the 2030s. I hope I'm still here to see that happen. Sure. Okay, sorry. Yeah, I will do that. No problem. Any questions so far on this part?
There is one here, 2 of them.
Do you have any sense of how the uncertainty principle comes into play in the measurement at these levels? Especially when you talked about measuring, I forget what it was here, some of those early measurements, you said, okay, we can measure at the atomic level. And of course, uncertainty comes into play somewhere down below there. And I'm already saying things I'm only partially familiar with or understand. But I thought I'd ask you if you have any insight into that.
No, I do not, to be honest. The uncertainty principle, which is Heisenberg's uncertainty principle, if the cat is dead or alive. I mean, that is a quantum calculation in terms of how quantum effects are affecting measurements. I don't think that it plays a significant role in this. I think it plays a role in terms of what are the influences of quantum effects on, for instance, the mirrors, the bouncing of the laser. And I don't know exactly how they calculate that. I don't know.
More question on your left.
I think I heard you say that these gravitational waves move very quickly. And then later on, you said they move about the same speed as light. Are they actually measuring that? And is there any correlation between the speed of light and the speed of gravitational waves?
So there are 2 things. The mergers of the black holes and neutron stars are happening very rapidly. Certainly in the last rotations of before the merger happens, that is happening very quickly. Gravitational waves, and they confirmed that with a measurement of two pulsars, so two neutron stars rotating around each other, they could see over time that the rotation of those two neutron stars was shifting. They were coming closer and closer together. And they could calculate from that coming closer and closer together that gravitational waves were lost because the energy went out of that orbit. And that confirmed basically Einstein's theory. For instance, there was a supernova explosion not too long ago where a star blew itself apart. Nowadays, with the technology, they are very quick in pointing all kinds of satellites to that event. So they could point exactly when the X-ray or the gamma ray or the UV light was hitting the detectors. And at the same time, Livingston saw a gravitational wave. So that basically confirmed that light and gravitational waves are moving at the same speed. Did that answer your question? Yeah. Part two. I mentioned in my intro that we only see 5% of the universe. The rest we call dark. And that's probably because scientists are not very inventive in names, or we have no clue what we are talking about. One is called dark matter, and the other one is called dark energy. So how do we come to that? And there is a model that's called the lambda CDM model. CDM is for cold dark matter. We're based on all kinds of measurements, and then we'll go through them. This is our current concept of the universe. So 5% of the mass we can see. Around 25% is what they call dark matter. Up till now, no dark matter, like no graviton, has been detected. There are tons of experiments going on around Earth to detect dark matter particles. The problem is that the theory is at the moment that dark matter particles are only interacting with gravity or with a weak force. If that's the case, it will be very, very difficult to detect them. A matter particle called axions is coming out of quantum calculations. They were already done in the 70s. And the WIMP stands for weak interactive massive particle. But nothing has been detected. We have very good evidence, and the Einstein rings are one of them, that dark matter exists. One of your famous astronomers, a woman, Vera Rubin, saw in the 1960s the first real observation of dark matter. Because what she saw is that a galaxy, like our own galaxy or an Andromeda galaxy, the stars that are rotate in that galaxy all rotate at the same speed, which is very weird. Because you would expect with the mass of a Milky Way in the center, that stars in the center rotate at higher speed than at the end of the spiral arm. It's taken way longer to rotate. I mean, that's what you see in our solar system, right? Mercury goes in 80 days around the sun. Neptune takes years to rotate. But it's not what they measured. And that's the first clue, basically, that in a galaxy, there must be way more mass than what we see if stars at the end rotate at the same speed as in the core. Dark energy is basically something from the 1990s. So we know that only for 30 years. There were two US teams, and both got Nobel Prize for that, that measured based on neutron stars. There's a specific concept on how neutron stars explode. And because of the intensity of the light and the concept they have, if a neutron star explodes here or 10 billion light years away, the light intensity is the same. So you can measure, based on the light intensity, you can measure distance and timing. What they found, since everybody thought space is expanding, we know the mass, we know dark matter, at a certain point in time that all will slow down based on gravity up till I don't know when, and then it will crush down together again. But what they found is that space is accelerating its expansion. So roughly the estimate for our universe is 14 billion years. About 5-6 billion years ago, our universe started to expand with a higher speed, which was completely counter to what everybody thought. That's where the lambda from Mr. Einstein came up again, because he had in his original general relativity theory a lambda in his quotations, and he said later it was his biggest mistake. Maybe he is still right, but ask any scientist what dark energy is, and we don't know. Is it the vacuum energy of space? Is it quantum fluctuations at space-time level? If quantum mechanics is calculating that vacuum energy, that space quantum fluctuations, then we are an order of 10 to the 120 wrong. So something is not right. So that lambda CDM model is basically our current mathematical model of the universe and our Big Bang. There's a cosmological constant, as I already mentioned, lambda, which is associated with dark energy. Cold dark matter, because if dark matter would be warm, would be hot, it would have high speed. It would show its energy, and we don't see it. And then we have normal matter, like you and me. The model is pretty good. I mean, you maybe read in some media that the James Webb Space Telescope is every day questioning that model. It's not the case. I mean, there's some fine tuning, definitely. We don't understand everything, don't get me wrong. But it has a very good understanding about the structure of the microwave background, the large scale structure and how galaxies got to be. What is very important, they can not only calculate, but also measure from the origin of the universe, the amount of hydrogen, helium, and lithium that were the first 3 elements to show up. All other elements are made in stars by supernova explosion. So the gold you have in your finger is coming from a star. So there was about 75% hydrogen, 25% helium, and a little bit of lithium. And the accelerating expansion based on the dark energy model. So this is a picture that shows the current model. Don't ask me the question how the Big Bang came to be, and don't ask me the question what was before the Big Bang, because we don't know. I don't know. Nevertheless, inflation occurred that has nothing to do with your grocery prices. That has everything to do with quantum inflation. Mr. Green, Brian Greene, American physicist, came up with a model because there was the question, how can it be that the universe looks completely flat? And if you go from the left side of the universe to the right side of the universe, why is it so smooth and has the same appearance everywhere and the same temperature everywhere? So he came up with a model of super fast expansion in the first second of the universe, where that all smoothed out. After that, we basically have, and that's about 375,000 years, what they call CMB, so the background radiation, and we have measured that. I will show you that in a moment. Then we come to the Dark Ages. There's nothing to do with the 1500s European Dark Ages. Has everything to do with, at that point in time, the universe cooled down enough to have hydrogen molecules, and hydrogen molecules absorbed and blocked all the light to go out. After the first stars were formed and with UV radiation blew out the hydrogen and ionized it, that's where the first stars came to be. It's about 400 million years. So this boundary, the James Webb Space Telescope can see, also because it is more sensitive for infrared light. And then basically everything came to be in terms of galaxies and humans and everything else, animals. Cosmological background. So this is the picture that the Planck satellite made about 10 years ago, which shows a very uniform picture. You might be surprised that I say that, but be aware, this is a picture where the average is 0. So we talk about minus 2.3 Kelvin as the temperature of the universe is. Red and blue is minus 1/10,000 of that temperature. So this is a very sensitive picture, which basically shows how uniform the universe temperature is, because these are minor fluctuations. Now, what they can calculate from these pixels is the growth of the universe and how dark matter influenced the expansion. Dark matter must have been present already at that time. Otherwise, we cannot see the structure in the filaments we see at this moment. The structure in the filaments was measured already by the Sloan Digital Sky Survey. That's a US-based, I think they're in Arizona, having a telescope as well in Chile. So what they measured were a lot of stars and galaxies and quasars. Quasars are very active cores of galaxies. A lot of data every night, but what you can see is a filament structure in how the universe is organized. That filament structure shows knots and shows voids. This is a computer simulation for the people that do biology here. This looks like neurons in our brain. But coincidence? Well, that's another theory, maybe another presentation. But this is a computer simulation where they show the voids and where dark matter basically organized the lumping of structures. And that's how, at this moment, we can measure and see the universe. You know, so these lumps of galaxies, we call them galaxy clusters. We are also part of a galaxy cluster, our own Milky Way. And we see this kind of buildup of the universe. So this is another sign of dark matter being present. You know, this is our local universe. You see all the different galaxies around us, and you see those filaments and the concentrations of galaxies happening. You know, here, those kind of concentrations. And we know that, for instance, the Andromeda galaxy is moving towards us, and Andromeda and us, we're moving to what they call the big attractor. That's M87, and that's a huge galaxy in the Big Dipper. We're moving towards that. So there is still concentration going on. There's another survey going on, still going, which is called the Dark Energy Survey. And I will show you in a moment how they measure that kind of stuff. But here again, you see that filament structure of the lumping of those galaxies and the voids. So what they measure is what they call supernova, type 1 supernova, that are the same candles of calibration that Adam Rees used for showing the expansion, the accelerated expansion of the universe. They also measure what they call Byron acoustic oscillations. Now that's a difficult word for ripples in space-time that are like sound waves penetrating our universe from the original Big Bang explosion. And then weak gravitational lensing. So I showed you already the Einstein ring. That same thing is happening when a black hole is moving in front of a star, so you can see the gravitational lensing. This is, by the way, our Milky Way. That's in the way of measurements because it is disturbing, it's too bright. This was the 1 millionth picture they took with this survey. So what they're looking at, and they do that with algorithms and artificial intelligence, they look at a picture like this and look at distortions of starlight from around those Milky Ways. And you see there are tons of galaxies in this picture. So they look at distortions in starlight around these pictures. And from those distortions, they map the dark matter. They map how the light got distorted in that picture to map out the dark matter. So there's basically the same thing like they do with the Einstein rings. I mentioned Vera Rubin already. They dedicated the scope to her, which I think is very good. And this will be a scope that is located in Chile, at Palantar, in the Atacama Desert, about 16,000 feet high. So you have very clear skies, dry, no water, never rains there. There are tons of telescopes over there. We'll start by the end of this year. Very wide field because they will picture every night, a lot of the night sky. Unfortunately, thanks to Mr. Musk and co, 40% of the data will be lost because of satellite tracks. 40% of the data. That's becoming a bigger and bigger problem. The biggest digital camera ever built, it was just installed, it was built in California. And they take every 15 seconds an exposure. A lot of data. They took a fiber cable from there to Santiago to hook it up to the internet. This is a picture of the telescope. Then we have Euclid flying at the moment, European, American, Canadian satellite. And it's next to James Webb and Gaia. Now, James Webb is looking very focused, right? Euclid has a very wide field, and again, same reason like the other wide field cameras to make bigger pictures, and you can every time see the diffractions and the changes in the sky. Special telescope in there. And again, a lot of data coming down from it. It's a 6-year mission. They will take a look at 1/3 of the sky, very high resolution, and about 10 billion objects will be taking a look at. Next to that, they will measure redshift, so they can see 3-dimensionally how those pictures are built up. They use what is called step and stare method. Most of the satellites that are mapping the universe do that like this. So they take a specific picture of the sky, take a snapshot, go further, take a snapshot, go further, and then a year later they come back to the same spot, so they can again see the differences. 2 cameras aboard. I will not go into the detail. One is for visible wavelength, and the other one is for infrared. Very precise instruments, and again, one is to focus on specific pictures with a camera on the night sky, and the other one, the infrared, is used for measuring redshifts and with that distances. You know, redshift, like blue shift. If you hear a police car go by with its siren on, that's what the Doppler effect is, and the Doppler effect also exists in light. So everything red, what we see red, is going away from us. Everything blue, like the Andromeda galaxy, we can measure the spectrum of stars in the Andromeda galaxy. They're coming towards us. It will be a nice show, by the way. In 5 billion years, when we merge with the Andromeda galaxy, that will be a starry night, I can tell you. We need to have clear skies, of course, in Michigan. That's the problem. What is always nice with those kind of satellite things, I mean, you know the famous story about the Hubble Space Telescope, where the space telescope needed some glasses in the beginning of the 90s because the optics were not good, and it was only microns difference between what it should have been and was. I am always amazed how they are able to fix problems on satellites. I mean, one other example is the Voyager. You probably know Voyager 1 and 2 were launched in the 70s, are out of our solar system at the moment. And they had a software breakdown on one of the Voyagers 6 months ago. It got repaired. And we should be proud because they had to take people out of their retirement and fix the software that they made at that point in time, because nobody was able to do that. So one of the things they discovered is that they could not see that clearly anymore after a couple of months. And it turned out there was ice on the mirrors. Well, obviously the vacuum in the scope was not that good. So they had ice on the mirrors. So they heated the scope from -147 to -113, and the ice disappeared and they're fine again. They also had a hole in the external sheet, which caused sunlight to come into the visual detector. And they pointed the telescope a little bit differently to avoid that. And as you can see, they were not very clear. These should be stars. It looked like the scope was drunk. But they had a problem with guiding, and they solved that with the gyroscopes. But again, imagine it's in the L2 point, so it is 1 million miles from Earth. And here you're sitting behind your laptop solving a problem, because there's no way to get out there. And that L2 point is the Lagrange point. That's named after a French guy who calculated that between Earth and Sun, there are about 5 points where gravity of the Sun and the Earth are countering out, and that's a preferable point to place a satellite there because you need very little fuel to stay where you are. So the James Webb is there, and so several other satellites. Yeah, this is still a talk about astronomy, so I wanted to end with some nice pictures. This is one of the pictures that Euclid took So here's the satellite, this is our Milky Way, and we will focus on one of the points that Euclid took a look at. So here's Euclid. So we're focusing in, this is the area we look at. This is this area, comparable the size of the moon, and we're focusing in more and more and more. And again, they are looking at, so this is the area we look at, this is this area. This is the size of the moon, and we're focusing in more and more and more until we're at the Milky Way or galaxy. And again, they're looking at distortions in those galaxy concentrations to see how the dark matter distribution is. This is the entire picture. I mean, it's amazing that they can make this kind of detailed pictures nowadays. I still know the times that I was laying under my telescope with a camera and bringing them to someone that could develop my film, and the guy telling me, I only see dots on there. I did not print them. I said, well, that's what I wanted, those dots. The Abel groups, Abel is also a US astronomer. These are galaxy concentrations. And again, they take pictures of these galaxy concentrations to look at all kind of distortions around those galaxies, how the matter is distributed in the galaxy. You know, these galaxy clusters, this is one of the famous examples. This is still a nice picture, M78. I took a picture of that on Sunday night when we had clear skies, but not as detailed as this one. But there's a price difference between my scope and that scope. But still a nice picture. And again, they look at matter distribution. Another famous cluster, the Perseus cluster. Again, lots and lots of galaxies concentrated, and those concentrations give a clear picture of the distribution of dark matter. Famous nebula. This is made by infrared because you see all the gas here that is heated up by a star in the background. This is part of the Orion Nebula. So they call this the Horsehead Nebula. All those blue streaks is gas that is being ionized by a bright star in the background of the Orion Nebula. And this is basically a copycat of our own galaxy. So as far as all the measurements are, we are what they call a bar-dominated spiral galaxy. So if I take a look at this galaxy picture, the sun is roughly here. So barred spiral galaxy with us, we would be here roughly. That was it. Thank you for your attention.
Thank you very much. Very informative for sure. Are there any questions?
We do have an online question from Larry, who asks, what is the current thinking about the possibility of dark matter consisting of neutrinos?
That's a very good question. The answer will come from a neutrino experiment that is at the moment being built in the US. Fermilab in Chicago is part of that. They're building a detector in a mine in South Dakota. Hopefully the detector is up and running by the end of this decade. Neutrinos are very interesting particles. They have mass, that is for sure, very, very tiny mass. We're talking in micro electron volts. At this moment, they come in 3 flavors. As I showed, we have an electron, a muon, and a tau, and each of those particles has a neutrino as well. They were puzzled for a very long time about neutrinos from the sun because they detected a too little amount. And it turned out over the last couple of decades that neutrinos are capable of changing from one flavor of neutrino to another flavor of neutrino. So they measured only one flavor and forgot to measure with the others. And with, you are bombarded by millions of neutrinos every second. So yeah, that is still a possibility. That detector is basically going to detect the mass distribution of those neutrinos, because from the Fermilab accelerator, they will shoot neutrinos through the Earth to that mine in South Dakota. What they will look at is the exact mass of the neutrino, the different flavors, and there's speculation about another neutrino, a fourth neutrino, that could fit the dark matter picture. So that is a possibility.
I remember reading in the last few months that as the James Webb Space Telescope looks closer and closer to the Big Bang, they're finding many more stars already formed than they thought would be there. Are there new theories or adjustments to existing theories that might explain that?
Like I said, the overall picture of the lambda cold dark matter model still stands. The timing on star evolution, even galaxy evolution, or black hole evolution, I mean, first of all, there's the measurement. We talk about 13.5 billion years away, 13.6. So it is the measurement itself that is still questionable. At the same time, the models for galaxies, certainly galaxy evolutions and also star, is not that refined yet that we know when it exactly started. I talked about the dark ages when hydrogen was penetrating the universe and light was not. But at that point in time, first stars must have been formed because it was the star light that ionized the hydrogen where the space became transparent. So I think we don't know yet enough. And that's why James Webb is there to find those things and refine our models, right? So I'm always excited to see the latest on that.
Are there any theorists, a la Einstein, Copernicus, yada, yada, in the offing right now? Somebody that's really coming up and people are saying, what's his take on things?
There are. And there are several US-based people. That's when you get when you're getting older, remembering names. There is at least Brian Cox from England is a very famous physicist. But there are a couple of Americans as well. Brian Greene is one. He also came up with the inflation theory. Thorpe, I forgot his first name. Thorpe.
Kip Thorne?
Yeah, he was also the one that was one of the people that got a Nobel Prize for the LIGO setup. So yeah, there are several ones. Are they all as bright as Einstein was? Not sure. They are still debating a lot about different theories, but the fundamental questions, and everybody acknowledges that, the fundamental questions on what really dark energy is, what is really happening at the quantum level, because our feelings are completely contradictory to what is happening in quantum mechanics. Richard Feynman, another famous physicist, said, when you understand quantum gravity, you have no clue, because it is so different. String theory is one theory that combines gravity and quantum. The problem is that there are 10 different string theories that do that. So which one is the right one? So at this point in time, on those fundamental levels, there is not one that really stands out and says, guys, you don't get it. This is it. No.
There are some questions over here.
Yeah, so does inflation violate the speed of light, speed limit?
The expansion of the universe is basically doing that. And you, with, yeah, correct, correct, yeah. But the expansion of the universe is doing that already. And that has nothing to do with the speed of light. The speed of light in the universe is still the speed of light, the maximum. But the expansion of the universe and also the inflation was way faster than the speed of light.
Karl, it's my understanding that the Japanese LIGO is actually underground in a mountain.
Correct.
Can you explain why they chose to do that?
That is the same with the Vigro in Italy. If you're underground, you have less problems with vibrations. And the other thing is cosmic radiation coming from the Earth is not affecting your measurements. That's also why they're building the South Dakota detector underground in a mine. I think it is 2,000 feet at least underground. So to avoid influence of cosmic radiation, because we are bombarded by particles coming from the universe.
A layman question. You're talking about 100+ years of research that you just described today. What are the sources of funding, ongoing funding for this research? What's the motivation behind it? And what disruptive forces are there potentially that could affect this research?
And you asked me that question without talking about politics, right? Yeah, no, that's true. In the United States, most of the funding is coming from the National Science Foundation. In Europe, there's a European consortium. I mean, ESA is 26 different countries. And also, if we take a look at CERN, which is a collaboration of 8,000 different scientists from around the globe, not only European Union, but also America, Canada, Japan, you name them, are involved in funding of that. Why do we do that? I think it is human curiosity to know more about our world. What I see a little bit of a problem, certainly for NASA, is the fluctuation of their directions. If I see the planning globally, that planning for, let's say, missions, also for CERN or Fermilab, you talk about 1 or 2 decades in the future. NASA almost is forced every 4 years to go from here to there and back, and that is not helping them. Let's put it that way. But still, in the science community, there's a tremendous amount of collaboration and cooperation globally. Also with the Chinese. Russians a little bit less, but the Chinese for sure, Japanese, India, Europe. There's being built at this moment a huge fusion reactor in France, which is a tremendous global corporation. It's probably the biggest building project ever done globally. I would not like to be the project manager there, but so yeah, it is still ongoing, but yeah, fearful for the future. At the same time, maybe some private enterprises, despite the fact that I don't like Mr. Musk, he's still triggers some new innovations. And going to Mars, it's not that easy. As humans, we are very vulnerable on a journey to Mars. I mean, think only about the amount of radiation we will have during that journey, or the amount of water we need to take. So it will not happen next year, for sure. But I mean, that's also where it is depending, and I think donations as well. People still struggle to. I mean, if we talk about NASA, their budget is not that big. It's 0.3% of GDP. In the Apollo time, it was 5-6% of GDP. And that 0.3% of GDP, and I love dogs, don't get me wrong, but a NASA guy told me that the amount of money they get every year is the same as Americans spend on dog food. So it's not that big. And I mean, that they have to set priorities clear. Do we need to do everything we want to do? No. Europe is discussing at this moment a collider that is 4 times as big as the current collider in CERN. Their questions are raised. When we spend 100 billion, what do we get out of it? What are the answers? At the same time, if you take a look at the technology now, or at your cell phone or Zoom, or that's all based on what we did in space and science and what have you. But yeah, I agree with you. There's worrisome. Yeah.
We have one final question. We'll wrap things up. And if you
Sure.
have further questions, we can do it afterwards. And last question.
Not really a question. I just wanted to mention that one of the members of our astronomy club, his name is Harold Rijkse, and he was quite a sophisticated astronomer who worked on the New Horizons spacecraft. It was the recent craft that passed Pluto. Was it 2017? No, 2018. Just want to put a plug in for the club, which meets the second Thursday of every month at Mactaw Bay Middle School, 7 p.m.
Thanks for the pitch, Peter.
Thank you, Peter. And thanks to our speaker, Karl. Dare I say it was enlightening. Thank you so much for joining us today. This was very informative, and I hope that you will be able to come back and join us again. Thank you.
Sure.